Solutions for the review mock for properties of curves. Number 1. The diagram below shows part of the graph of the gradient function y equals f dash of x. So don't be confused. This is not the function. This is the gradient function. They did not give us the function. Okay, what do they want to do now? On the grid below, sketch a graph of y equals f dash dash, clearly indicating the x-intercept. This is a lot like the investigation that we did. So all we need to do is, estimate the gradient at each point, and then we will graph it below. Because this is f dash, and what we're graphing here is f dash dash. So all we need to do is take the derivative of this, and then we're going to put it down here. So let's see. If we take the derivative here, we're going to get a horizontal slope or gradient, which is 0, right? What about here? It's a positive slope. Maybe let's say +2 or something like that. What about here? We could say it's like -2 going down. Okay, it's going up. All right. So now let's graph it below. So at the Q point, it's 0, right? At the P point, it's like +2. And at the R point, it's like -2. And then we could just connect these, assuming that it's going to be a smooth curve. And guess what? It's a line. Okay? This should bring back memories of the investigation for the mosaic investigation and the most recent investigation about the water slide. Complete the table for the graph of y equals f of x. So what is the x-coordinate for the maximum point of f? What is the x-coordinate of the inflection point of f? And remember, they have not given us a graph of f itself. They've only given us f dash and f double dash. But we know that the stationary points of f yield a derivative of 0. So like, for example, I'm going to mark them here. So here's a derivative of 0. Here's a derivative of 0 of f itself, right? So at P and R, there are stationary points. These two stationary points, P and R, they might be minimums, they might be maximum, or stationary inflection points. I'm going to make a sign diagram to try to figure this out. So we know that at P and Q, the derivative is 0. And in between them, the derivative is positive, and on the sides it's negative. We're just looking at the graph here and making a sign diagram from that. Now what about the second derivative? The second derivative, we're going to draw a sign diagram for that too. P, Q, and R. And at Q there's a 0, and at to the left of the Q it is a positive value, and for the right of Q it is a negative value. And now we're going to figure out, okay, what about our two stationary points? So we can tell from looking at the concavity at this point, which is P. So at P, we can see that the f dashed is 0, and the f dash dashed is positive. So that means it's concave up. So the shape of the graph is here. I'm going to do it in a different color. So it's like concave up here, and then here it's concave down. So which one of these brown points is a maximum? It has to be this one, right? Because at this point, it's concave down. So at R, it's concave down. So let's see, that's the maximum. So we know it's R. P would be a minimum, right? Because at P, it's concave up. Okay. Then it says, which is an inflection point. Well, it's not P or R because both of these are at concave up or down places. To have an inflection point, it needs to be concavity 0, which is here, right? So what point is this? Remember, this is Q. So at Q, there is an inflection point because the concavity is 0. And if you look at F dashed, it's not a stationary point. So it is an inflection point, it's just not stationary. So we'll say Q is the inflection point. And then we'll say, the reason why we say that B part 2 is Q is because the F dash dashed is equal to 0 at x equals Q. So that's how we know that it's an inflection point. All right. Number 2. On the axes below, sketch a curve, y equals f of x, which satisfies the following conditions. Okay, so from -2 to 0, which is this region here, f dashed is negative and f dash dashed is positive. So it's concave up, but the slope is negative. So it would have to be something like this. Oh, yeah, something like this. Okay, so this is concave up, but the slope is negative, right? What about the next point? It says x equals 0, f of x equals -1. Oh, they're giving us a point here. It goes through this point here. Okay, so we drew our curve in the wrong place, so we'll adjust it there. And at that point, the derivative is 0. Oh, that was lucky. I made it flat here, see? Okay, and f dash dash is positive. Okay. And it looks like f dash dash continues to be positive even from 0 to 1, so I'm going to continue that. Oh, and look, they marked a point for us. 1, 2 is on the graph. Okay, so it continues to be positive up to 1, 2. So we use that information. It says the f dash is positive between 0 and 1. Yeah, we drew it positive also. And then we marked 1, 2, and it says f dash continues to be positive there. And then finally, from 1 to 2, f dash is positive and f dash dash is negative. So the concavity is now down for this region here, but the slope, the gradient, is positive. So that means that it kind of turns over like that. So here's an inflection point. Okay, so it looks kind of like this. And wow, that's it. Okay, so let's go on to number 3. The diagram below shows the graph of, finally number 3. The diagram below shows the graph of x squared e to the minus x for the domain 0 to 6. There are points of inflection at A and C, and there is a maximum at B. Okay. Use the product rule for differentiation. Find f dash of x. So we're going to find f dash of x of that. So let's say that u is x squared and v is e to the minus x. So u dashed is equal to 2x. V dashed is equal to negative e to the minus x. Now let's use the power rule and differentiate. So we're going to have 2x, which is u dashed, times v, which is e to the minus x, plus u, which is x squared, times v dashed, which would be e to the negative x negative. Okay. And then we can put this in the answer box here. Okay. So we did the product rule and found f dashed. Okay, now find the exact value of the y coordinate of b. Okay. We don't even know the x-coordinate of b yet, so it's kind of hard to find the y-coordinate. We do know the function, so we could figure out eventually the y-coordinate if we knew which x-coordinate made this maximum. Now that's a hint there, maximum. So that means if b is maximum, that means the f dashed at this point is going to be 0. So how about if we find the derivative? Hey, we already did find the derivative. It's in a. Okay? So we have the derivative 2x e to the negative x minus x squared e to the negative x. And we know that that is equal to 0. That's where that would give us the point at b. So let's see, when is this equal to 0? So let's factor out the e to the negative x. That might help us. I think it will help us. E to the negative, using the zero factor property, one of these factors needs to be 0 to make the whole thing 0. But e to the negative x is never going to be 0. Okay, the smallest it's going to be is a very small number, very small positive number. It's never going to be 0. So what about the rest of this? 2x minus x squared. When is this 0? Well, there's two solutions, so don't get excited that x equals 0 makes this makes it 0, because we need to find another solution too. So we're going to factor out a x, and then we have three factors. We have e to the minus x, we have x, and 2 minus x. So any one of these being 0 can make the whole thing 0. E to the negative x, as I said, is always positive. So when would x be 0? Well, when x equals 0. And when will 2 minus x be 0? Well, when x is 2. So the two critical points, or the two stationary points for the function are 0 and 2. And so obviously 0 is this one here, okay? And then, so this must be 2. This point here must be x equals 2. Okay. So if this is x equals 2, what is the y-coordinate of b? Well, then we just take the original function, which is x squared e to the minus x, and we can substitute in x equals 2. What does it give us? 2 squared e to the minus 2, which is 4 over e squared. Okay, so that, and they say exact value, so they don't want to put that in the calculator or anything. 4 over e squared is the answer they're looking for. Alright, now since the second derivative of f is f dash dashed, and then it gives us this function here, how nice of them to do the derivative for us, because I wasn't looking forward to taking the derivative of that. Use this result to find the exact value of the x-coordinate of c. Remember that c is special because it's an inflection point. Remember that inflection points do not have necessarily a gradient of 0 or f dash of 0, but the f dash dash, the curvature, is going to be 0 right at that point. Because remember, like when you have a cup shaped down, then it's a negative f dash dash or second derivative. And when you have cup shaped up, then it's positive. So you can see, looking at this thing, since A and C are the inflection points, that the middle part is curvature down and the outside parts are curvature up. So how do we make sure that C is an inflection point? By taking the second derivative, which they already did for us, and showing that at that point it is 0. The curvature is 0. So all we need to do is set this expression to 0. E to the minus x is equal to 0. And when does this happen? When does this happen? It happens at the point A, and it happens at the point C. So we're going to try to find all the solutions and figure out which one is A and which. We know that e to the negative x is never exactly 0. It could be very small, but it's never 0. So our only hope is x squared minus 4x plus 2. We want to try to factor this, and by factoring it, hopefully we'll find the x coordinates, which will make this 0. But of course, it's not an easy factoring to do because I don't think the factors are integers. So that means we can't do a regular factoring. We're going to have to use quadratic formula. Okay? All right. So b is going to be negative 4. And c is going to be 2. And a is going to be 1. So let's see, negative b would be negative of negative 4, which would be positive 4, plus or minus the square root of b squared, which would be 16, minus 4ac, which would be times 2 times 1, all over 2 times 1. Okay, So that gives us 2 plus or minus the square root of 16 minus 8, which is 8 divided by 2, which is equal to 2 plus or minus 8 is actually square root of 2 times 2 times 2, right? So actually that's equal to 2 square root of 2 over 2, so the 2's cancel out, and we're left with 2 plus square root of 2, or 2 minus square root of 2. So those are the two points, A and C, and obviously C is the smaller one, or I'm sorry, A is the smaller one, it's to the left, right? So it would be that one, and this would be C, which is the smaller one. So the x-coordinate of C is going to be 2 plus square root of 2. Okay. And I think that's it. Number 3 is the last one. Yep.